Hey everybody. So we're going to march on creating some more rules for taking derivatives. And as you can see, we're going to do the trig derivatives today. So what we're going to start with is investigating the derivative of sine and the derivative of cosine, and then we'll use these to build the rest of them. Okay, so it's a good moment. We'll let's take a look at where our trigonometric functions come from. We've got our unit circle. We'll just do a really quick reminder of how the trig functions work. So I've got a unit circle here. It's got its the radius of 1 centered at the origin. And then I've got my horizontal line out along the positive x-axis. That's one side of our angle. And I can increase the angle here, right? So now I'm letting this ray rotate what we call the positive direction, counterclockwise. And so for any angle, right, so that little dotted line in there, I'm just representing the angle, maybe we'll call it theta. For any angle, we look at where this line intersects the unit circle, and the x coordinate is going to be the cosine of that angle, and the y coordinate is going to be the sine of that angle, right? And this is how we get beyond the confines of thinking of trig in terms of triangles, where you're locked into angles that can't really be bigger than 90, because then you don't have right triangles anymore. With this, we can go all the way around, right? And then we can, of course, keep going. I don't have it programmed to keep going, but you can imagine we can continue to rotate. And so we get these trig functions, which end up being really powerful because they're really useful for modeling things that have cycles, right? Things that are periodic in nature, among other things. They show up all over the place. We're going to be working in radians, right? The derivatives, our calculus works better with radians for the trig functions, though it's not horribly hard to convert, but for now we're just going to stick with radians. Remember, radian measure is just how we measure an angle in radians is on this unit circle. It's the ratio of the length of this arc. We say the arc subtended by the angle. So all that means is if you look at, let's put one more point in here. Let's put 0, 1 on our circle. Oh, sorry, I meant 1, 0. So that's where our angle starts. And then where it finishes, the portion of the circle between those two dots, that's the arc subtended. If you take the ratio of that to the radius of the circle, which in this case is just 1, so it seems weird to take the ratio and divide by 1, but what it does is it divides out the units of length, right? Because angles aren't going to be measured in meters or centimeters or feet or whatever your circle is measured in. And so we end up with a unit that's really just a ratio. It doesn't really have a unit to it, right? It's just a number. So the radian measure, like 1 radian, means that we are the same length as the radius, right? And then with this in mind, we get angles like straight up. Our right angle is going to be pi over 2, which I can't quite land on. Straight line angle is pi, all the way around is 2 pi. So anyhow, we'll always be working in radians unless specifically mentioned otherwise. So there's our unit circle, right? Now, how does this lead to the graphs of sine and cosine that we're used to? Here's a nice animation of this, right? Cosine is shown in blue on top here. It tracks the horizontal movement of, right? There's this unit circle down in the bottom here, in the bottom right corner, right? And so as the angle goes around, the cosine is tracking its horizontal movement. Now it's translating it to vertical movement, right? That's why they have this nice bending line to show you how that works, because the horizontal axis of both of these cosine and sine graphs is telling us how big the angle is. So as we go along horizontally, we're increasing the angle, and cosine tells us, the height of the cosine graph tells us the width, how far away to the right or left from the center that dot is on the circle. And then the sine tracks its y-coordinate, how far up and down it is, right? And this demonstrates really clearly why these two graphs are pinned between -1 and 1. That dot is living on the unit circle, so it can never go further than that away. Okay, now back to derivatives. So we want to investigate these two derivatives, sine of x and cosine of x. Let's look at a graph to start getting an idea about the derivative of sine. So here I've got cosine graphed in red and sine graphed in blue. We've hinted at this idea in some earlier videos, but what I want to do is I've got the tangent line to sine, right? I can show us various tangent lines as I scroll along the graph. And what I want us to notice is a couple of things. So let's start here. At this value of sine, at this point in the sine graph, we're at about pi/2. The tangent line appears to be horizontal, which would be a slope of 0, right? Notice that the value of cosine there is also 0, right? And as, whoops, I did not want to zoom in like that. There we go. As I move, I don't know why it keeps jumping. As I move along the sine graph from this point, notice it starts sloping upward, right? We're curving up, and the tangent lines become, I swear I'm not touching a thing when it's jumping like that. I think I'm doing, oh, there's like a gesture control on that I'm not used to. Okay, sorry about that. I'll try to keep my fingers very still. But in any event, as we notice what's happening, so I'll go back to 0. We started at a horizontal tangent with the slope of 0. As we move in this direction, the tangent lines are becoming steeper, and we notice the values of cosine are becoming steeper. And right here at the origin, we've explored the idea in the past that sine of x looks very much like the function x near 0, meaning it has a slope of 1, right? Y equals x is a line with a slope of 1 that goes to the origin. Notice the value of cosine at 0 is also 1. So it appears that, at least qualitatively, sine and the slopes of the tangent line of sine seem to be moving in the same directions as the values of cosine, right? So now, let's keep going a little further. We're at this steepest part of the sine graph. Now, as we move forward, we're still positive. We still have positive slopes, but notice our tangent lines are getting less steep. They're getting closer to flat, meaning their slopes are getting closer to 0. At the same time, we see cosine values moving down towards 0. And when we hit this point here where we appear to have I can't quite hit it, but we can imagine a horizontal tangent line right around where cosine hits the x-axis, where its value is 0. Now our tangent lines appear to be sloping down, negative, which is exactly the values of cosine. They stay negative. They get less negative as our line gets flatter. And right when we get a horizontal tangent, cosine gets back to 0. So it's feeling like cosine is tracking the slopes of the tangent line of sine, right? We haven't proved this, but man, this feels like a pretty close relationship, right? We could do this in reverse. We could look at the slopes of the tangent lines to cosine. For instance, if we look at the tangent line, say here, where it appears to be horizontal, we see the value of sine is 0. On the other hand, here, where the slope of the tangent line appears to be very steep and negative, sine is in the positive direction. And here, where the slope of cosine appears to be very positive and somewhat steep, sine is in the opposite direction, is in the negative direction, right? Negative values. So it's almost the same relationship, except it's kind of backwards, right? We're missing a negative in there. So let's take a closer look at these more analytically. Let's actually go through and try to prove one of these derivatives. So I'm going to take a look at the cosine derivative. Oops. Most of the texts I've seen will do the sine derivative, so I'm only going to do one of these. They're very similar proofs. Let's do the cosine one, since I think the sine one is more readily available out there if you want to see it. Let's take the derivative of cosine of x. And I'm going to remind you of two limits that we've proved in the past. We've proved that the limit as h goes to 0 of sine of h over h is equal to 1. And the limit as h goes to 0 of cosine of h minus 1 over h is equal to 0. So we investigated these earlier in this lecture series when we were doing limits, and we're going to make use of them now. Okay, so we'll start with the definition of the derivative, right? So the derivative of cosine has got to be the limit as h goes to 0. We do the cosine of x plus h minus the cosine of x all over h. Okay. Let's do some manipulations of this thing outside the limit. So I'm just going to come over here and do some scratch work. Cosine of x plus h. Well, there's a trig identity, one of the sum identity. This is the cosine of x times the cosine of h minus the sine of x sine of h. Okay, so that means cosine of x plus h minus cosine of x can be written as cosine of x times cosine of h minus sine of x sine of h minus cosine of x. I can reorganize this and write cosine of x cosine of h minus cosine of x minus sine of x sine of h, and then factor that cosine of x out and get cosine of h minus 1 and then minus sine of x sine of h. Okay, so this is nice. What I've done here, notice, let's get a different color. Let's try blue. Notice I've got this cosine of h minus 1 here, which looks like what we have up there. And I also have a sine h, right? And they're both over h, which is handy because we've got an h in our denominator here. So let's do a little bit of work around that now. Cosine of x plus h minus cosine of x over h, I can now write as this expression over h. All over h, and then I can just do, we can use the properties of fractions and rewrite this as two fractions. Oops, cosine of h minus 1 over h minus sine of x sine of h over h. And then one more thing I want to do, rewrite both of these fractions in a convenient way. I can think of this as cosine of x times the cosine of h minus 1 over h minus sine of x times sine of h over h. Okay, so we used one trig identity, and then the rest is just basic algebraic properties and how fractions work. But notice again, what I've got in here are these two nice limits, two nice expressions that we know the limits of, right? And then I've got cosine of x and sine of x. Those are going to be easy to deal with because this is a limit about h. It's asking what happens to x or cosine of x as h goes to 0, nothing, because h isn't in there. And so this will these are the cosine and sine of x will be treated like constants in terms of the limits. All right, I'm going to take this new expression and put it in here. So I'm just replacing everything, this cosine of x plus h minus cosine of x over h with this new form that I wrote it in. We've got cosine of x times cosine, let's make it very clear, times cosine of h minus 1 over h minus sine of x times sine of h over h. Now we're going to use some limit properties. I can take the limit of each of these terms individually. The limit as h goes to 0, cosine of x times cosine of h minus 1 over h minus the limit as h goes to 0 of sine of x times sine of h over h. And now again, we want to think of cosine of x and sine of x are constants as far as h is concerned. Changing h has no effect on them. It doesn't appear in that expression. So I can slip via another one of our limit laws that cosine of x out front and that sine of x out front, right? Passes right through the limit. Now we have precisely the two limits that we have up above, right? This one with cosine of h minus 1 over h, that limit goes to 0. So this whole first term disappears. And our second term, we have minus sine of x, sine of h over h goes to 1 as h goes to 0. So all we're left with is minus sine of x. And so let's move this just a little bit. All right, sorry about that. I didn't plan quite well enough. The derivative of cosine of x is the opposite of sine of x, right? That was what we noticed before, that when cosine was steep and positive, sine was negative towards its max. And when cosine's slopes of tangent lines appeared to be negative, sine was positive, but the values seem to match up just in this flipped way. And that's exactly what this shows us. So there's our cosine derivative. There's a very similar proof for sine that I will leave up to you, which also matches with our intuition that there wasn't this flipping happening, that cosine was tracking the slopes of the tangent line of sine. Okay, so these are two big derivatives for the trig functions. If all we remember are these, we can get the rest of them, which we'll do in just a minute. But we have to know these, right? And the trickiest part is remembering one of them comes out negative, the other one doesn't. Okay, let's remind ourselves exactly what this means. If we want to know the slope of the tangent line to sine at any point, we evaluate the value of cosine at that same input. And if we want to know the slope of the tangent line to cosine at any point, we evaluate the sine at that point and take the opposite of it. So let's do one quick example. Let's say I want to find the tangent line to y equals sine of x at x equals, let's do pi over 4. Okay. So to find the line, to the equation of a line, we need a point and a slope. Start with the point. Well, we know exactly what point we should use. We should use the point, the input pi over 4, and the output sine of pi over 4, right? Whatever that value is. Well, if we remember our unit circle, we can replace right, or pi over 4, sine of pi over 4 is root 2 over 2, right? So I'm picking a convenient angle that we know the value of sine there. So there's our point. We need our slope. This will be the value of the derivative at x equals pi over 4, right? So the derivative of sine of x, we just saw cosine of x, and cosine of pi over 4 is equal to root 2 over 2. So the slope of the tangent line at x equals pi over 4 is root 2 over 2. So let's write the equation of this line. We want y minus y1 equals mx minus x1. So we'll have y minus, so our y coordinate is root 2 over 2. Our slope just happens to be the same, right? There's nothing that just doesn't typically happen. And then our x coordinate is pi over 4. And this gives us the tangent line at the point x equals pi over 4. So let's look at that on our graph. So let's just put that line in. Y minus square root of 2 divided by 2 is equal to the square root of 2 divided by 2 times x minus pi divided by 4. So let's get some of this stuff out of here. Let's get rid of cosine for now and this other traveling tangent line. So there's our tangent line, right? And this looks very, very correct, right? At this point, they intersect pi over 4 root 2 over 2, right? These two graphs look exceptionally similar, right? So we zoom out, we see that there are some differences, and the further away we get, obviously they look very different from far away, but in close, that red line is a very good approximation to the blue curve, right? And that's what we want our tangent line to do. Okay, let's do one other example with taking these before we've taking a derivative with sine and cosine. But this time, let's make it a little more complicated. Let's see what happens when we combine these with one of our other rules. So let's just write these again. Derivative of sine of x is cosine of x, since these are new, and the derivative of cosine of x is negative sine of x. Let's see what happens, for instance, if we have a function that's involves a trig function, but something else as well. So let's take f of x equals cosine squared, sorry, x squared times cosine of x. So to do this derivative, we're going to need to use the chain rule, or sorry, the product rule, right? Because we've got the product of two functions. We've got x squared times cosine of x. So remember our product rule. We take the derivative of the first function and we leave the second function alone. And then we take the derivative of the second function and we leave the first function alone, okay? So this first derivative, we can use the power rule. The 2 comes down, we have x, and we have our cosine of x. Then this, we get the derivative of cosine is negative sine of x, and we leave x squared alone. So we end up with 2x cosine of x minus sine of x times x squared, okay? For some reason, I hate having that x squared after the sine, so I'm going to rearrange this. There's nothing mathematically necessary about what I just did, but for whatever reason, it just bugs me to have sine of x times x squared. I like having that x squared out front. So there's the derivative of this function, right? So now we've added a bunch of power to our set of tools, right? We can now take these not only derivatives of the trig functions sine and cosine, but we can expand that to combinations of sine and cosines with the functions we know how to do already, like polynomials. All right, let's do another example. Only this time, let's try to take the derivative of another trig function that we haven't shown anything of, we haven't proved anything about yet. So right now, this seems tricky, right? Maybe we have to go back and use a bunch of trig identities and use that limit definition, but we don't. We can actually use one trig identity, the definition of tangent, or one way to define tangent, as the quotient of sine and cosine, right? That's one way we can define space. There we go. The tangent. Now we have the quotient of two functions and we have a quotient rule. So let's go ahead and use the quotient rule. So to take the derivative of a quotient, remember we take the derivative of the numerator minus the derivative of the denominator, and leaving the numerator alone, right? And then in the denominator, we're going to get, we get cosine, we square the denominator, right? I'm just gonna take a little moment to remind us that cosine squared of x is equal to cosine, the cosine of x, the whole thing squared. It's not equal to both of these, those are the same. This is not the same as the cosine of x squared like this, okay? So I wanna make sure we understand that difference. So in any event, here we have our quotient rule. So now let's go ahead and take these derivatives. We know the derivative of sine is cosine, and then we've got this other factor of cosine. The derivative of cosine is negative sine. And we're all over cosine squared x. So this first term becomes cosine times cosine, or cosine squared x. We've got a negative and a negative, so we're gonna get a positive, and then we have sine of x, so we have sine squared x all over cosine squared x. We're going to use another trig identity. Cosine squared plus sine squared is 1. And all we have in the denominator is cosine squared of x. This can be written a little bit more neatly as, right, remember that secant of x is just 1 over cosine of x. So this thing becomes secant squared x. And so we have that the derivative of tangent of x is just secant squared x, right? And so we just used, we used a couple trig identities. First, just the definition of tangent, and then this Pythagorean identity, cosine squared plus sine squared is equal to 1. And then we use at the end, we just rewrote, right, again, using the secant definition, what this 1 over cosine squared is. And we've got tangent. So all of the trig functions can be written in terms of sine and cosine, either as quotients of them, basically. Sometimes it's 1 over 1, which we can still use the quotient rule, or in the case of tangent and cotangent, sine over cosine or cosine over sine. And we can do something like this to all of them. And so the result is, because we have the sine and the cosine derivatives, we have all of the derivatives of our basic trig functions. So let's just write them all down. So here's the ones we've done so far. We just saw tangent of x is equal to secant squared x. And we have, let's see, we have cosecant of x is equal to negative cosecant x times cotangent x. We'll have the derivative of secant of x is going to be secant x times tangent x. and then the derivative of cotangent of x is negative cosecant squared x. Okay, so these are good to know, and when you work with them a lot of these will start to stick in your brain. I would say tangent, the derivative of tangent and secant tend to be the most familiar with me. I see them most often out there in the world, but it depends on what you're doing, what you might see more often. But really, if you know these two, you can always use the quotient rule. To get these other derivatives. When you use it, and I'll leave those up to you guys. We did the tangent one, you can do the other ones on your own. You might not get something that looks exactly like this. For instance, when we did tangent, we ended up with 1 over cosine squared and then decided to write it as 1 over secant squared. There's nothing wrong with 1 over cosine squared. That's a valid interpretation of the derivative. But it's just traditionally people write it, it's a little simpler to write secant squared. Same thing might happen when you take these other derivatives. You'll have something that doesn't quite look at like what I've written down here, but if you've done it correctly, there's some manipulation using trig identities and definitions that will get it, that will let you realize it's the same thing written a different way. So you can't always come up with these. Okay, I think that's going to be it for this one. We'll do some more examples in another video, but these are our basic trig definitions. Which is great. We're really expanding what we don't. These are really important because it's really difficult to take, or can feel pretty daunting to take the derivative with the definition of the derivative. You know, the proof that I did wasn't super long, but I kind of knew where it was going. If you didn't know where it was going already, if you told me to take the derivative of tangent using the definition of the derivative, I don't know that proof off the top of my head, except to use the quotient rule here. I'm confident we could find some trig identities that would make it doable, and we'd have to probably find some new limits that we have the values for, but it'd be doable but complicated. But instead, we have the sine and cosine, and we get the rest. And so now we can expand our differentiation rules to all the trig functions. Okay, that's it, everybody. Thanks very much. I will see you next time.